Cool. Good afternoon. My name is Rory McKinley. I work at Epson. At Epson, I'm the leading practitioner of apology-driven development. So the new framework we try and do, write code, you deploy it, you write it back, and you spend the rest of the day saying sorry. It's a bit out there. We hope it will take off. And on that note, I'm supposed to read a message from Concurrency. Sorry, it's the last minute. Dear Rubyfuza attendees, you guys, if you write Ruby and promise not to break stuff, speak to Louise, and she will give you Rory's job. Okay, so don't speak to Louise. Speak to me, Rory. So today we're doing a very rough guide to Ruby concurrency. You can think of it as a highlight reel. When I started this, I thought, I'm going to struggle to find enough material for 20 minutes. And now I realize there's just way more material than I'll ever be able to fit in any presentation, let alone 1 to 20 minutes long. So moving on. So concurrency is a way to structure a program by breaking into pieces that can be executed independently. Just keeping concerns separate, and that seems fairly reasonable. And you think, okay, I can understand that. And then you get to the bit where concurrency is not equal to parallelism. And from now on, I'm referring to that as the P word, because I'm pathologically capable of saying parallelism more than 2 times in a 20-minute period, so it's the P word. So concurrency is not equal to the P word. And I thought, oh, that's interesting. Parallelism, that's my 2 quotes, is programming as an execution of possibly related computations. And yeah, that didn't help me either to understand the difference. So the best analogy that I've seen so far is juggling. And I spent 2 weeks practicing, so I could give you a juggling demo to help things along. It turns out if you're a noob, you shouldn't start to change things. And please don't ask me how I know this. It's very embarrassing. So if you think of a juggler, the average juggler, they'll have lots of balls in there, but they'll only ever be holding onto one. So they have multiple concerns, but they're only ever working with one. So that's concurrency. Concurrency often looks like parallelism. But that's just because you're not fine-grained in it. Whereas parallelism is if the juggler was handling 2 balls at the same time. So all in each hand and lots of balls in the air. I hope it helps. That worked for me. So we're going to be looking at just concurrency. So that I'll pronounce the parallelism thing. And the obvious benefits of concurrency, the usual one you see, is it reduces the impact of I/O bound operations. So start with a long I operation, usually over the network, and you can switch off to something else while you wait for the operating system to tell you that it also encourages the use of solid engineering principles. If you start to go crazy with your code that's concurrent, you're likely to get into trouble fast. I'm going to spend the rest of my career trying to disprove this, but that's the theory. And then the next big thing, if not the current big thing, is horizontal scaling. Where is no longer giving us faster and faster CPUs, so the challenge is to store across CPUs with multiple threads per CPU or distributed systems like the Amazon Web Services. And that's going to be very hard to do if you're not practicing concurrency in your code. So the main players in Ruby, or the most popular ones, are thread, forks, and now fibers in Ruby 1.9. And we're going to look at briefly the highlights package for each one of those, and the code we're going to use as a sample is what I like to call the stupidest web client imaginable. So starting off with threads, the wiki gives 2 descriptions. A thread of execution is a small sequence of program instructions that can be managed independently by an operating system schedule. Sounds very impressive. I like to think of it as a lightweight process. But essentially, it's the smallest block that your operating, or you can think of it as the smallest Lego block that your operating system wants to interact with. So here we have our web client. It's not too impressive. It goes through a collection of URLs, and for each one of them, it spawns a thread. It does a write to fetch asking to fetch some data. It gets the data back, and then it exits. It doesn't even do anything with the data, so it's really pretty stupid. And so some things are immediately obvious. You know, scoping threads works pretty much like scoping blocks. So a block that's been passed a method for. It starts executing as soon as you finish defining it. So as soon as we go out of each iteration of the loop, that thread is started and it's running. And at the bottom, where it gets interesting, you have a blocking call. So generally, when you're running these threads, you want them to complete before your script exits. And that's not always intuitive because the threads are doing fairly long operations, whereas the rest of your code is moving at relatively the speed of light. So that's going to move past those threads, and if you haven't got something to catch it, they're going to exit. So what we have here is a collection of threads which we loop through, and we call tjoin on them. And tjoin, so thread join, is a blocking call. So it will stop and wait for the current thread to complete before it processes the next thread. We also have a guard in there, so you don't try and join the current thread. So the current thread is the parent thread. That's kicked all of this off. If you don't have a guard in, both Ruby 187 and 193 explode in your face with different messages. So, you know, I don't know, you'd think that if they know it's going to explode, that they'd just work around it. But that's what it'll do. The interesting thing as well, which a colleague mentioned yesterday, is threads silently accept or swallow exceptions. So if your thread exception's out, unless you explicitly told it to abort an exception, it won't do that. But if you've got to either call to thread join or thread value, at that point you will see the exception. So it's pretty non-intuitive, and it's something else that can catch you off guard. So other things about thread, awesome facts. Threads are preemptively scheduled. That means the interpreter decides when it's going to switch between threads. It tries to identify calls that would traditionally be blocking calls and switch to another thread. You can game the system. So there's options to tell the thread it's okay to handle somebody else, or you can set the thread priority. So no one who's actually, if you read about that, no one suggests that it's a particularly good idea to do. So your mileage may vary. And then the thing that always catches us with threads is thread safety. There's portions of the Ruby code base that are not thread safe, from something as humble as puts. If you're trying to do debugging with puts in threads, you're likely to get results that entirely don't look like what you expected. And then there's always the issue of variables and race conditions. So this brings in the case of mutex, which is a topic that will probably keep me busy for more than 20 minutes. Something has been covered in the previous talks today, so I don't have to explain a lot about it. In MRI Ruby, so the C-based Rubies, you don't get any parallelism at all. In Ruby 1.8, that's because of green threads, and in Ruby 1.9, it's because of the GIL, or the GVL is the other name for it. But you do get parallelism in MacRuby, the 2.0 branch, Rubinius, and JRuby. And then in Ruby 2.0, are we expecting awesome stuff for threads? I'm not sure. There's been people campaigning for the removal of the GIL. I don't see any evidence that that's going to happen. And there are other sort of trains of thought that are asking for changes that will make it easier to defreeze objects, to make them more easily immutable. I'm not sure if that's going to happen either. So there's a bit of a question mark on Ruby 2. So our next player is forks. And to fork a process is to make an exact copy of it. And even in saying that, I'm actually lying in some operating systems. Because some operating systems practice something that's called copy on write. So what copy on write does is if a parent creates a child process, initially they share the same memory. So you don't have a doubling of resource usage. And the operating system, when it determines that one of the processes is about to write to that memory, will create a copy, so that you don't have each process copying each other's memory. And that's something that we'll touch on again when we look at how Ruby supports forking. So forking, the internals of what you do in the TCP socket is the same as for threads. You're going through a collection of URLs again, and you have the fork call, and what you do is you pass to the block, and the code in the block only gets executed in the child. It doesn't get executed in the parent. And at the end, we have a blocking call again. So process.waitAll tells the interpreter to wait until all the child processes have completed. And that's generally, again, a useful thing unless you're planning on starting up something like daemons. WaitAll will return a collection of process IDs and statuses, and there's variants of it that you can wait for a particular process or detach a process if you really don't care about it. Now, fork has some other interesting behavior if you don't pass it to block. So the code above, you've got an if fork and an else, and if you were to run this code, you'd see that both branches of the if are being exercised, which is a bit weird. And so what happens there is fork when it's called, so remember it makes an exact copy. So if you call fork without a block, your parent and your child process both start executing at the point that you call fork. The difference is that in the parent process, fork returns the process ID of the child, and in the child, it doesn't. So what you'll have is in the parent, fork returns a truthy value, and you get to produce the top bit, and in the child there's nothing, so you go into the else. But what will happen is the puts right at the bottom, both of them execute that because they're executing from the same point. That's possibly the second weirdest thing about forks that I've hit so far. The weirdest thing for me is pipes. So pipes we're pretty familiar with if you do any work on a Linux operating system or Linux-based. It's used to pass data from one process to the other, and you can use it within your Ruby code. And when you call IO pipe, you create a set of descriptors, one for the read end and one for the write end of the pipe. And so again, what you have when you call fork, you get a copy. So the child has a copy of the read and write end, and the parent has a copy of the read and write end. And so they can use this to communicate. So what the child does in the block of code, it closes the read end, because you can only have one end open at a time, and then it will write some stuff down the pipe and closes that end. And the parent on the other end isn't interested in writing, so it closes the write end and it reads from the child. And so that gives you a richer interaction between the parent and the child than you can just get from looking at exit statuses. This is something that's incredibly hard to test. So forks, remember the copy on write. So the copy on write, we've heard lots today about mark and sweep. Copy on write is defeated by the garbage collector in Ruby 1.8.7 and in Ruby 1.9. That's because the garbage collector, as was covered actually in the talk just before, marks the memory that it's going to leave behind, but that mark is seen as a write by the operating system. So as soon as the garbage collector runs, the operating system goes, wow, you've written to a lot of memory, I'm going to duplicate that for you, so we don't share. I know, right? Yes. But so, guys familiar with REE? REE, that's one of the things they fixed, is they made the garbage collector copy on write friendly. The bad news is, as far as I know, there's still no 1.9 branch of REE. The guys don't think it's worth carrying on with. So if you want to be copy on write friendly, you're a bit stuck until you get to Ruby 2.0. Ruby 2.0 has a new garbage collector called bitmap marking that doesn't actually touch the memory that it's busy checking. So it's copy on write friendly, and much happiness will ensue. Fibers. The fibers is relatively new, and the interesting thing is if you look at both Max's book and the Pickaxe book, both of them seem to treat fibers as this really low-level thing that most people will never have to interact with. Significantly pre-Goliath days, and fibers have become a lot more popular since then. And generally, a fiber, the official wiki definition is it's a subroutine that allows multiple entry points for suspending and resuming execution. It's effectively a restartable prop. You can call it when you want to, and you can exit from it, and then you can start it where it left off. And the examples I'm going to give of fibers really don't do it justice. There's people doing some really clever stuff with fibers. I mean, the Goliath is, I think, the poster child at the moment for fiber usage. And they don't even really use it for concurrency, and it's more a case of nice readable code. But if you look at some examples like Dave Thomas from Prog has done some clever things. There's some interesting examples out there. So we'll start off with the basics. Again, this is a little bit more complicated, so I'll split it up into a number of slides. We start off, we create a pool of sockets just by running inject, and we assign the key for our hash is a socket, and its value is a fiber. And the fiber is going to execute the read and write. So inside the fiber, we've got stuff that looks very familiar to what we saw with forks and threads, except there's two new things. We're passing in the writing socket as an argument to the block. And sort of in the middle there, we've got socket underscore R equals fiber yield. So fiber yield, in one instance, can be thought of as something similar to yielding in a block. It's relinquishing control to the calling fiber. And at the same time, it also serves the purpose of being able to transfer data in and out of the fiber, which we'll touch on a bit later. But for now, what it's doing is it's writing, and then it's going, OK, I'm done. Carry on with someone else until we see that the socket has data available for reading. And then at the end, we have our equivalent to the blocking call that we've been doing for threads and forks, except this is a bit of a cheat. To check for, you'd probably be better off checking for sockets that are available for reading or writing. But then I don't get a chance to show you fiber.alive, so it's a little bit gross. So what we're doing is we're going through all the fibers that we have in our socket pool, and we're seeing if any of the fibers are alive. So a fiber is alive when it doesn't have any more, when it still has code that it needs to execute. So in our case, this is a shortcut for its fibers that either haven't written or they haven't read yet. Then we get all our sockets that are either ready for reading or writing, and then we resume our fibers. And this isn't the world's most readable code, I apologize. But effectively what you're doing is finding each of the fibers that are associated with the socket, and we're giving the fiber the socket again. So the first time you call resume, whatever you pass to resume becomes the value that gets passed into the block. So that's only the first time. So the first time we pass in the socket from the right group, it becomes socket underscore W. The next time we call resume, the value that we pass into resume gets passed as the return value of fiber.yield. So when you call fiber.yield in a fiber, it stops execution at that point. When you call resume on it after you've yielded, it starts executing at that point, and its return value can be assigned to a variable. In this case, the reading socket. And for me, fibers, if you can grok the way stuff goes in and out, then that's pretty much it. They really are fairly simple. The API is tiny. And that's possibly why people do so many awesome things with it. So another example which might make it a bit clearer, we've got a simple fiber that adds some arbitrary numbers together. The first time you call resume, you pass in 0. So in the fibers, num is assigned the value of 0. And fiber returns the value of num plus 1. So the return of resume is 1. Then we call resume again, and this time we pass in 5. So 5 is the value is assigned to next num. Because that's the return of the first yield call. And then we add 2 to it, and we return it, and so the return value of the resume call is 7. And that's really as simple as it's really just toggling on and off. Another thing that makes fibers cool is that they can actually interact with other fibers. And to demonstrate this, we've got 2 fibers, both of which are referred to as, so F1 refers to F2 as the other fiber, and F2 refers to F1 as the other fiber. And we've got a whole bunch of text interleaved. And so we start off by resuming F1 and giving it F2. So we say to F1, you start, and your other fiber is F2. So F1 will print hello, and then it will transfer control to F2. And when it transfers control to F2, it will also transfer itself so that it can see what the other fiber is. And then effectively what you have is ping pong. They'll jump between the two. Each transfer call acts exactly the same as a yield. It will switch control, and when it gets back, it will continue from where the transfer was, and then you end up with the sentence at the bottom, which is essentially a combination of the 2 fibers running together. Fibers have a 4K stack. That doesn't refer to how much data they can contain. It really is a rough analogy for how many local variables you can keep in a fiber, so approximately 4,000. There are patch requests in to have this limit be something that you can dynamically assign at the start of runtime. Apparently the guys, especially doing stuff like XML parsing, where they rapidly exceed 4,000 local variables. Fibers are pretty awesome in C-based Ruby. In JVM and Rubinius, they're referred to as poor man's fibers because performance isn't quite up to the level of C-based Rubies. And generally, the proponents of fibers, one of their arguments is that fibers are a lot faster than threads because there's no context switching involved. Yeah, I haven't seen an example to disprove or prove that. And so on the ending note, I don't slide off without making any sort of commitment or statement. The question is, which one do we use going forward? We've got the options of fibers, forks, or threads, and I'm going to give you a definite answer because I'm that kind of guy. The answer is yes. Depending on what infrastructure you've got, so if you're running JRuby, for instance, you probably would find something, a combination of threads and fibers useful. If you're running Ruby 2.0, then perhaps forks and fibers will do it for you. And the interesting thing is a lot of the guys, there's 2 guys that are quite big in the Goliath community. One guy's Ilya Grigoric, and the other guy's a guy by Mike, I think it's Karam. Both of them advocate actually a combination. They're looking to have changes in Ruby that will allow combinations like this because one thing fibers don't give you is they don't give you parallelism. They just give you concurrency. And that is pretty much it. Thank you very much. Any questions? Awesome. Stunned you into silence. Thank you.